Now, this video is good if you've got optical isomers in your exam. Sometimes they put in complex questions, they'll put molecules that you might not be familiar with, and I've seen that recently in a quiz for past paper exam questions I put together. You're usually used to the amino acids, and the chiral carbon, if it's in the data booklet, will be in these red circled areas here each time. But you need to be able to recognize that there are 4 different groups coming off the chiral carbon regardless. And in this experiment, I ended up using sucrose, which I'll tell you later why. And if that was an exam, you'd have to recognize there's 1, 2, 3, 4 chiral carbons there. And if you rotate that, that actually is something else that's not glucose. Now, another important thing for biology is these amino acids must be in this form, which is the L form. Otherwise, your body can't use them to make proteins. And same with the all the other ones. So the carbohydrates, you can't use the L-glucose. They all have to be Ds to make the starch. And so that has implications for evolution arguments as well. The randomness of having these perfect DNA, protein, carbohydrate systems come together in one cell that can replicate. That increases probabilities infinitely almost. So that's an argument for the biology side. For the chemistry side, you just need to be able to recognize the chiral carbons. The second thing you need to get from this video is experimental tinkering, I guess. For the experimental questions, you need to think about why things don't work and how to improve them. And most exams at this present moment are rapidly increasing the number of experimental questions, which is good because that's what science is really about. And so the polarimeter, I'm putting this as a physics experiment, even though it's really chem, physics and bio, because it's got a polarimeter in it. So I'm just updating this video because I think I've found a reasonable explanation on how light is turned by the molecule. So that's either has to be a pure L or pure D. It has to be the pure left-handed or right-handed molecule. And so first of all, the one source just points out that when you have a linear polarized light, you can mathematically deconstruct it to left and right-handed circular polarized light. And so if you add this one here and this one here, it reaches this point. And so if you add that top point over here and to this one over here, this bottom one, it's over here, and vice versa. So that one, it basically, if you add them together, it will equal this one. So this one can be broken up into this one and vice versa. And now that's fine mathematically, that you could do resultant vectors, but you need to know whether that's actually true or not. So if you have a proper polarimeter and some better equipment, they have shown that if you do add, say, this one here at this angle and then one at 90 degrees to it, it does actually add up in real life. The two waves do interact with each other and form a 45-degree angle. Now this is electromagnetic radiation, and they're only showing you the light, not the magnetic one. Sorry, the electric wave, not the magnetic wave. And so there's a wave here and a wave here, and this one, there's a wave here and a wave here, and then they're on this angle. So just for simplicity, they're just showing you the electric fields. And so they've shown that to be true for adding waves, and they've also shown it to be true when they do it out of phase. So if you do it out of phase by a quarter, and you can mathematically add these together, and you do actually experimentally get a circular or polarized wave. Obviously, you'll see in the video that my setup is not going to be able to do that. Maybe it can. I should talk to the physics teachers. And so this particular one, so I saw another source that said if it's a spring, it doesn't matter if it's going this direction or this direction. It's a left-handed or right-handed spring. And so if you have a collection of molecules, as long as it's pure, it doesn't matter which direction the molecule's in. It's always going to turn it in the same way. and so the index of refraction is higher for a left-handed or a right-handed, and so the molecules interact with the linear polarized to create the left and right, and then one of them has a higher index of refraction, so is slower and out of phase, which creates the turn. This one's just saying that one is absorbed better, so it's not a phase; it's an amplitude difference, and the amplitude difference causes the resultant vector to be more lopsided to a left or right-handed circular polarized light, causing the angle change. And so, as I said before, the other one said that there's an index of refraction, slowing it down, making the phase change that causes the left or right. It doesn't matter. It might be both. It might be one or the other. The fact is these resultant vectors are legit. They're not just mathematical. That's how the waves actually interact and come out the other side. And so that's how it turns it. So what I initially did was actually got a little bit lazy. So what happens here is when you I just used white light, and I think I used a cuvette. And when you polarize light with one polarimeter, I just use sunglasses, 2 lenses of a sunglass, and it polarizes it in one direction. And if you put another lens, the second lens out of my sunglasses at 90 degrees, it blocks the light. And so if the substance that was my little handmade polarizer here, and so that should, at 90 degrees, there should be no light. If the substance can turn light, so I did put some amino acid in there, tryptophan and tyrosine, and that, I'll give you the numbers in a sec. If that turns light a certain number of degrees, one turns to the left, one turns to the right, you should be able to turn this, and so it either blocks it out or lets all light in. You can measure the angle by how much it has turned it, and your reader will turn it to show that light gets through. So the maximum light that gets through or doesn't get through, you can relate that to the control. All right, I'll do a control a little bit later with the final setup. Okay, so if I'm just going to the second setup, so the initial setup wasn't working that well, and so I looked up what's more ideal, and so they said, well, shorter wavelengths don't turn as well, so use a yellow filter. So a yellow filter contains green and red, so I threw a filter in there, and I grabbed just my lens, just my sunglass lens. So the other thing I looked up, this one's ChatGTP actually, is if it's actually going to work. So the other issue was, even though the amino acids did turn quite well, tyrosine and tryptophan, you can see in this table here, sucrose was way better. It had a much larger rotation. And the real issue was the fact that you can see, if you rearrange this formula, the observed rotation here, it's the specific rotation times how long the path was, which was around 10 centimeters, which is the standard, so that was fine. It was the concentration. And so if it's A equals specific rotation times C times L, if you times those up to here, because this is what I'm observing, this A up here, then the concentration was a real issue. And because these two are not very soluble, the max concentrations over here, I wasn't going to get any significant rotation. I'm not going to be able to see a fraction of a degree, whereas the sugar here is like 200 times more soluble, and so you can see a massive rotation. And the other issue is once you rotate above 180 degrees, if it's really long, you're not going to be able to know how much it's rotated, but I'll get to that in a second. So that's another issue as well. So what I have here is, if I just jump to the actual result, you can see as I turn the lens, I am getting close to 90 degrees, and this is I think this is the sugar at the moment. I am getting all of the yellow light to disappear, and that's at close to, it seems to be a 45 degree turn. I'm getting a 45 degree rotation. and that's with a dilute solution. So that could be accurate. It could be about half of the saturated solution. And so I'm thinking that's working because the yellow is getting blocked out, which is definitely the green, but then the red still comes through. And when I do it at 90 degrees, the red comes through. So that is the correct answer, is maximum blocking. And the maximum blocking seems to be at 45 degrees. So that seems to work, although I can't tell because I didn't take a concentration reading, which is an issue for several reasons. So I made a syrupy solution and tried to get the max rotation of maybe 60. But then I found when I put it into the test tube, there were crystals in there and it was just too close to saturated. So I diluted it with some water, maybe at 50% or so. And so then I upped the game a lot more and I used just like a pure red laser. And I didn't want to be looking inside the laser. That's because it's not safe. So I used just a camera, a webcam, an expensive one that costs as much as a laptop. But, this school provides it, so that's fine. And then I used I went and raided the physics. Well, I did for the laser as well. I went and raided the physics department and got some Polaroid lenses with actual... I can turn and see the angles, and I tried to go for a measuring cylinder this time, so that I could actually see. It's actually flat, so it's not bending that on that side as well. And so I'm just testing it, so you can see that when I turn this at 90 degrees, the light completely cuts out. So that's my control, and it does work. It's about 10 degrees off, which is important because I'm going to try and take a measurement now. And so I just keep turning that. You can see when it's at 90 or 270, it blocks out, but it's out by 10. So I'll just remember that, and minus 10 from whatever answer I end up getting. Okay, so now I'll move over to the final one. So me not knowing whether it's 90 or 270 is an issue. And so now I actually use the real substance, and you can see, I'm going to slowly turn it. You can see there's you'll see a little white line come up. So that's 100% through, and then it sort of cuts out here, which is 110. And it's meant to cut out at 90, but there was 10 degrees out. So I'm thinking I'm getting a 10 degree rotation. And so the issue is I'm not quite sure if that's a 10 degree rotation, or whether it's 110 or 190. I'm not sure how many times it's rotating. So I think a solution to that would be make it in different solutions, dilute it out, and so maybe go up in and use the formula and go up in 10% concentration differences or something, and then I can see a gradual change in the rotation of the light, or I could have removed some of the liquid in increments of 10, so maybe go 10 centimeters, 9, 8, and do that as well, because that's probably a lot easier, and do the calculations and see if the turn is matches the calculations, and that would confirm how much it's turning. So me doing not actually doing a range of 5 means I can't really tell what's going on in the relationship. So that would be the biggest improvement to see whether this is working or not. And also me not actually measuring out what the actual concentration was. I kind of did a saturated solution and diluted it by at least 30 to 50%. Okay, and that would confirm whether this actually works or not. So I'm not 100% sure it works until that's done. And so that's the lesson to learn, guys, how to fix things, adjust them, look for the weaknesses, and how to do further improvements. All right, on top of that, you could be asked some random questions about some molecule never seen before and be able to recognize how many chiral carbons there are. Okay, so make sure you watch these videos. They are not just making you smarter and true scientists, they will actually help you on your tests, which unfortunately you guys care about more often, but that's the way it is.